Okay, so welcome back, and today we are going to discuss the idea of neighborless. So, in the last class, just to remind you, we discussed about thermostats and what do units mean, and today with the idea of neighborless, we shall be able to significantly speed up our computer simulations of molecular dynamics. Before we start neighborless, let me give you a bit of background. Now, as you know, in molecular dynamics, you are basically accessing different microstates and you are integrating Newton's equations of motions. Now, to get relevant statistical quantities, you really need to run the simulations over extremely large number of iterations. Typically, the minimal numbers would be something like 1,000,000, because even with the simple Lennard-Jones interactions, the particles have to move around, each microstate has to be accessed, which is significantly different from the previous microstates, and only then can you take a snapshot, or you can take that microstate and from that extract relevant statistical quantities. And of course, to get a relevant and good average, you need to access large number of microstates, so that your averaging is good and you can compare with your thermodynamic quantities. So, you are basically calculating thermodynamic quantities by taking suitable statistical averages, and for that you have to really run the simulation for extremely large number of iterations. And if you have suppose around 5,000 particles interacting with each other in a simulation box, the way I have discussed in the past, where each particle basically you check for the distance between each pair of particles. So, if there are n particles, then you are basically checking whether the distance between a particular pair of particles is lesser than r c or not, and this distance checking you have to do for n into n minus 1 by 2 numbers, and only if the distance is less than r c, then you calculate the potential. So, whereas it might seem that you are saving the calculation of potential for a large number, or the force. So, you are saving the calculation of the potential of the force for a large number of particles. If suppose this is your particle I and this is your range of the interaction r c, the potential is cut off at r c, and what you are doing for this particle, you are also checking the distance between this particle and this particle, say, right, and this particle and this particle, say, and this particle and this particle, say, and only if it is less than r c, well, you are calculating the potential. But this calculation of distances between this particle and this particle is not of any much use, right. I mean, your distance calculation is important, I mean you have to do it, but if somehow the number of pairs over which you are checking for the distance between this particle I and the other particles, if the number of checkings of distances, whether it is less than r c or not, could be reduced significantly, that would result in a significant speed up of your computational code, right. And to explore this idea, I would like you to focus on this, and suppose this is a particle I, okay, and it is surrounded. So, there are only, suppose only around 3 particles, this and this within your cutoff distance. Now, after one iteration, this particle would have moved, right. How much would it have moved? Now, if suppose dt is 0.005, the integration with which you are integrating the Newton's equation is dt equal to 0.005. If your kbt was 1, that is what we have fixed till now, you can change it of course, then the average speed of these particles would be order of 1, for half mv square equal to kbt. So, it is order of 1. So, in one iteration, the average displacement, the expected displacement of say particle I here would be around 0.005, right, which is significantly smaller than the diameter. And if you consider 100 iterations, even 100 iterations, each particle is moving, but if you just focus on particle I, it would have moved from here to around a distance of 0.5 v dt into 100 iterations, right, 0.005 into 100, which is around 0.5. This is not much. It is not much compared to the it is basically half a diameter, right, if sigma equal to 1, significantly smaller than the size of the box. So, this particle would have moved some small distance from here to here, right. So, this particle, so it was, this particle was within its radius cut off. So, it was interacting, there was a finite force that it was feeling from this particle. After 100 iterations, it might have moved half its radii, where this particle, ith particle, is not interacting with this particle, but now it is interacting with this particle, right. It is a consequence of the motion, but still particle I is not interacting with this, all these particles, and however, you are calculating the distance between this I and all the other particles, and similarly each particle and all other particles, to figure out whether it is experiencing some force. It will experience some force if the distance between particle I and its neighbors are less than r c, right. So, the question is, since in even 100 iterations a particle I moves relatively small distances, can we somehow do away with the calculation of distances with all these particles which are much farther away from the particle of interest, here I, and if we do not need to calculate over the distance of particle I with this large number of particles, we are basically saving computation time. And neighbor list allows you to do exactly that. Okay. So, that is the motivation for neighbor list, or how one should think of the neighbor list. Now, let us get down how a neighbor list is calculated. Okay. Now, suppose this is particle I, I have basically taken the same figure which was in the previous slide, and this is your R c. And these three particles are within this are within the distance r c at time t equal to 0, say, right. Now, at time t equal to 0, you draw another circle or sphere if you are in 3D, you go of radius r s. R s, this S stands for the word skin, and the radius of this larger circle, which is definitely larger than r c, is r c plus a certain delta r. So, from here to here is delta r. Okay. So, you basically make a list of all particles which are within this distance r s. You do it at time t equal to 0. And for the next 100 iterations, when you are calculating forces on particle I, okay, when you are calculating forces on particle I, you do not calculate the distance of all the particles which are in the simulation box and particle I. Instead, you calculate the distance of all the particles which are within distance r s. And if the particle, if the neighboring particle, if a neighbor of I is within distance r c, then you calculate the force. What are you saving? You are checking, you are calculating the distance between a much smaller subset of particles, only those particles which are within distance r s, right, and not all the particles in the box. And within that small subset, you are choosing those particles which are actually interacting, which are actually within the distance r c. So, you have saved a large number of calculations. Of course, you are going to ask that this particle I and each particle in turn on which you are calculating the forces are going to move around in space. So, if this particle at time t equal to 0 was here, it is going to move here after some time, and similarly all the other particles are going to move around. So, the particles which are within distance r s, which are basically called the list of particles which are the neighbors at time t equal to 0, that is the neighbor list of neighbors which are in close proximity. You have to update that list, say every 100 iterations or every 500 iterations or every 50 iterations, depending upon the speed and depending upon the interaction. So, you have a neighbor list at time t equal to 0. After time t 0 plus 500 iterations, you are going to make another neighbor list, again calculate which particles are at distance r s, within the distance r s from particle I, but now particle I is in a new position after 100 iterations, and of course, all the other particles are also moved around. So, you have a new list of particles, and for the next 100 iterations, again instead of calculating the distance between particle I and all other neighbors, you just calculate the distance between particle I and the neighboring particles which are at time t plus 500 iterations. That after 500 iterations, you again call the neighbor list. You have a new list of particles which could be neighbors. So, for each particle I, and I can run from 1 to n being the total number of particles, n part if you like, number of particles, you will have a list of particles which are in its immediate neighbors, and you do not expect this list of neighbors to change within the next 500 iterations. 500 iterations is just an example, depending upon the physics of the problem it could be 100 iterations or 50 iterations. But you do not expect a particle which is sitting here, right, they are not moving at relativistic speeds or anything, they are classical particles, you know their temperature, you know their Maxwell-Boltzmann velocity distribution, and and if you have 5,000 or 10,000 particles, you do not expect extremely high velocities or speeds, and you do not expect a particle which is sitting here to come suddenly to come very sharply and straight towards this particle and start interacting in the next 500 iterations. Of course, this particle could interact with this, but then this has to move in this direction say, and this has to move in this direction, and it would take a few thousand iterations before these two particles could come in proximity and start interacting with each other, right. So, this is all that I have discussed here. This is so basically from a larger list of particles, from n particles, you are making for each particle I runs from 1 to n, you draw a circle which is larger than R c and make a list of particles with which it could interact in the next a few iterations, and every say 500 iterations you actually check the distance of a particle I with all the particles in the box, and from there make a subset, call it NS if you like, corresponding to skin. So, a smaller list of particle, and with the next 500 iteration do not do a distance calculation over all the particles, just do a distance calculation over the small list and figure out which particles it is interacting with. Even so, as it move in the next 500 iterations, it could move from here to here. So, it starts interacting with this monomer and does not start interact with this monomer, but it is unlikely that it is going to interact with this monomer. So, every 500 iterations you are basically updating the neighbor list. Now, if NS, so what do you get? So, every 100th step you were doing n into n minus 1 by 2 distance calculation. Now, you have a smaller list of particles NS, and for the next 500 iterations, say you are actually the number of distance calculations you are doing is n into ns by 2 instead of n into n minus 1 by 2, and if ns is significantly less than n, you save computation time, right. Now, the question comes is, okay, so what should be the value of R s? How big are you going to choose R s, right? And for that, to ask this question, what should be the value of R s or delta R, and how to choose that delta R? Here, let me tell you as a motivation of how to choose, what should be the logic to choose delta R. Now, suppose for a particular particle I, you have 10 particles within R c for particle I, right, at a certain time, and however, you have chosen a relatively large value of delta R. So, that R s is significantly large. I mean, it is much smaller than the size of the simulation box, but still it is large, and so that n s is 100. Suppose there were 1000 particles in the simulation box, and instead of doing a check of n into where n is 1000, n into n minus 1 by 2, you are now for 499 iterations, you can live with n into n s, where n s is 100 distance calculations. So, you are already saving a factor of 10 distance calculations, right. So, that is good, you have saved a bit, but if n s is 100, so even when, so in this figure, so from n s you have actually the particle I is interacting with only 10 particles. So, even you for the next 500 or 499 iterations, you are checking for the distance for these extraneous 90 particles, right. I mean, of course, some of them. So, right now it is interacting with certain 10 particles. After say 100 iterations, it could interact with a different set of 9 particles, because they would have moved in space, because all the particles would have moved in space, but still you are calculating the distance between around 90 particles extra, right. So, that is costly. However, if you chose delta R to be relatively smaller, so that R s is smaller, right, then n s could have been, so n s could have been say 40, and that is again a factor of 2.5 speed up from where n s equal to 100, right. So, basically you have chosen a smaller value of R s, which would in turn lead to a smaller value of n s, say 40, right. So, it is this case, but in that case, since R s is small, within your 500 iterations, right, this particle I could itself move and come here, so that it would start interacting with this set of particles, right. So, if you chose R s to be small, then you have to update your neighbor list, the list of neighbors, more frequently. Instead of 500 iterations, you have to do it every 100 iterations. Now, calculating a neighbor list, where you have to do a n into n minus 1 by 2 distance calculation pair. So, that is the number of pair of neighbors, and you have to calculate the distance. That is an extremely costly step as well. So, if n s is too small, you save on your each force calculation. You do not have to calculate over 100 neighbors, you can calculate over just 40 neighbors maybe, and actually the particle might be at a certain point of time might be interacting with only 8 or 9 neighbors. It depends upon the value of R c, of course, but then your neighbor list calculation becomes more frequent. On the other hand, if delta R is large, so that R s is large here, then you can call or update the neighbor list less frequently, but then in each force calculation you are basically calculating over a large number of neighbors, extra neighbors, whereas the particle is actually interacting with only 10, and that is an extra cost. Message. So, delta r cannot be too small, delta r cannot be too large, both will so of course, having an neighbor list will speed up, but it will not speed up optimally. So, you will get the maximum speed up or the optimal speed up if delta r is chosen in an optimal manner, right. So, if it is not too large and if it is not too small, and for every problem and density and dt and RC, one has to check out how much should one choose RS, so that your calculation or your speed up is the maximum. Okay. So, that is first part of the thing. Okay. So, the question is how to choose the value of delta r, okay, so that it is optimum. Suppose you have already decided that you want to update your neighbor list every 100 iterations. 500 is too much because the particles are moving, because basically you will have a large value of RS. So, sorry, RS and thereby NS. Now, if you are updating your neighbor list 100 iterations, how should you choose the value of delta r? For that, we basically take the help of statistical physics, Maxwell-Boltzmann distribution. So, here I have plotted the probability density of velocity or sorry speed, right. So, the probability speed distribution, Maxwell-Boltzmann speed distribution, PV dV by dV, and on the x axis you have speed, right. So, this is the magnitude of speed, and of course, there is a peak like this, and you might know already that the position of the peak, if you just revise your kinetic theory of gases, the position of the peak is at root 2 kBT by m. So, just revise your statistical mechanics and you will know that the position of the peak is at root kBT by m, reminding you that kBT we have chosen to be 1. We are measuring every energies in units of kBT, and m is also chosen to be 1. And if you have any confusion about this aspect kBT, what does kBT equal to 1 means, just refer to the previous class where we have discussed units. So, the position, so if kBT is 1, then basically this velocity, the speed at which you have the peak is at around 1.44 kBT. And what is the V average? Just to remind you from your kinetic theory of gases, it was 8 kBT by 3 m. So, 8 by 3 is approximately equal to 3, and square root of that is 1.7. order of magnitude. Of course, only if 8 was 9, you would get square root 3, but that is what the order of magnitude is, that is what the approximate value is, right. And if you have around 1000 to 5000 particles, you would see that you hardly have any particle which has speeds of greater than 5. You might find a few, very few. But of course, as you increase the number of particles, if instead of say 1000 or 5000 particles, you had a million particles, then you would find some particles for very rare occasions to be moving with speeds of 5. I did not mention the units. You should refer back to the units to understand what speed of 5 means. Coming back, so if you had million particles, maybe you will find some very few particles moving with a speed of 5, but hardly any particles moving with a speed of say 10. In these units where sigma equal to 1, and I told you how what time equal to 1 means in terms of kBT, m and L, right, in these units. So, what is the message? So, the message is the maximum speeds that you are going to see if you have around 5000 particles is around 5 or 6, not more than that. Okay. Now, you are updating your neighbor list every 100 iterations, say. So, you do not want your particle I to have moved so much in your 100 iterations that a particle which is another particle which is at a distance greater than delta r, okay, would have come and start interacting. So, basically delta r is the maximum distance, is an estimate of the maximum distance that a pair of particles could move relative to each other in the 100 iterations, so that they start interacting. Interacting means less than, distance becomes less than r c. So, basically r should be the maximum value that the relative speeds, if suppose two particles were moving absolutely at very high speeds towards each other, right, and this particle was not. So, this is your particle I and this is your particle under consideration. So, this particle should not in 100 iterations, if it is not within the neighbor list, if it is not in the neighbor, if this particle is not in the neighbor list of this particle I at time t equal to 0, then in the 100 iterations it should not come close to each other in the next 100 iterations, so that it starts interacting, right. Of course, if suppose this moves here in 100 iterations and this moves here, then this particle will come within the neighbor list, then your distance calculation will be there, and if it is, if they are interacting by a certain force, that would be calculated. But if this particle was here very far away and not within the distance r s at time t equal to 0, this should not start interacting within the 100 iterations, because you are not calculating for the distances, for the distance between this and this for the next 100 iterations, if this particle is not within the neighbor list, right. It is only after that you are going to do a recount that which particles are close to me, which particles have a potential to interact with particle I in the next 500 iterations, say. So, basically delta r is a measure of the maximum displacements which are possible in the 100 iterations, and you should choose delta r significantly large, so that within the 100 iterations no other particle which is not accounted for, which is not in the neighbor list, starts interacting with the particle I. And the way you would do it is, suppose one of the particles, say I, has let us take the maximum velocity, has around 5 times v average, right. Beyond that you are not going to find particles such high speeds. If you have 1000 to 1000 particles, 5000 particles in your simulation box, and suppose another particle j was also moving at an extremely high speed 5 v average, and they were moving towards each other. So, the relative velocity would be essentially a factor of 2. So, 10 v a v. Okay. So, in 100 iterations with 10 v a v being the average velocity, what is the maximum displacement, what is the maximum change in relative positions that can happen? That is, that will be 2 into, because two particles relative velocity 5 v average into 100 iterations, right, into dt, because v into dt is displacement, right. This is for the maximum velocity, this is relative, and in 100 iterations what is the maximum displacement that can happen. So, this is what would happen in one time step, right, or sorry, this I have made a mistake here. So, there should be a dt also here. And since there is a factor of 100, that is what how much it would move in 100 time steps, and delta r should be greater than this distance. So, the point is delta r keeps an enough margin, so that a particle which is far away does not come in and start interacting within the number of iterations over which you update your neighbor list. So, you should update your neighbor list suppose every 100 iterations, and then this is the maximum distance that the fastest pair of particles can travel, can reduce the distance between each other, and delta r should be at least greater than this number.